Theoretically, at least.
Why theoretically?
I just mean I've equipped you with the tools, but I don't know what that means. All right. So today we want to discuss the last identities. So we're gonna introduce to you. These are called the multiple angle identities. Okay. There are 3 sets that we're going to introduce to you today. We're going to show you the double angle identities, the power reduction identity, and the half angle identity. The first set of identities that we're going to show you are the double angle identities. These are the ones that you just derived in the warm-up today. The proof goes like this for sine of 2u. It's the one that I guess Caden did that one. Thank you, Caden. Cosine of 2u, you could write this way, which is, I think, how Tammy did it. Nice job, right? You could also write that this way. Can you convince yourself how that comes out? And you could also write it this way. Can you convince yourself why both of those are equivalent? Yeah. Think about it. And it's pretty quick to see that that's true, I think. And then the cosine of 2u, it's still written on the board. We might actually want to combine those just for the sake of brevity. Isn't that just 2 tan u over 1 minus tan squared? And now let's put them in a box. There they are, the double angle formulas. But please, do not keep these in a mental box inside your head in a different place than you store the identities we learned on Monday. These are still just immediate corollaries to the things we looked at on Monday, aren't they? Just immediately, I mean, the proofs are almost not even worth mentioning, are they? You just, sine of 2u is the sine of u plus u. Use the sum addition formula. It just falls right out. 2 sine cosine, those kinds of things. And we're not sure which of these 3 forms we like best for cosine of 2u, so I don't know. Take a pick, we can't decide, so we'll write them all down in the box. There are times when one might be more useful to us than another, so. So there's the first set, and I'm going to give you 2 more sets of identities in a box today. They are worth putting in a box, even though they're like basically the same identities we learned on Monday, just reformulated a little bit, because they just come up a lot. In particular, think about the fact that if someone asked you to graph the function f of x equals 2 cosine squared u x minus 1, like this. So if someone said graph f of x equals 2 cosine squared x minus 1, could you do it? Yeah, you could. If you just realize that that's the same as cosine of 2x, you'd be like, yeah, I know how to graph cosine of 2x. It's like normal cosine graph, just with period of pi. So I mean, already you can kind of start to see where maybe that, that's kind of contrived, but I can make that less contrived, and we can do some interesting things with that already. The other thing that this makes me think of too is that sine of 2u, for instance, or something like that. Well, we'll save something for the next slide, for a couple next slides here. So, double angle identities. Moving smartly along, let's talk about the power reduction identities, or the power reducing identities. We'll see whether these are useful in our lives or not. We can decide whether that's true or not. I don't know. But let's just go with it and see whether we like the algebra I'm throwing up on the board here. So I'm going to start by using one of the identities we just talked about, and that's one of the formulations for the cosine double angle formula. You see that from the previous slide? I just copied and pasted. Okay. And then I'm going to take that and I'm going to solve it for sine squared of u. So if I rearrange things so that I'm solving for sine squared, I get that. So far, so good. Okay, so that's called the power reduction identity for sine squared, for sine. Right? That is to say, if you ever see a sine squared in life, and you're not interested in dealing with squared trig functions, you can rewrite that instead. 1 minus cosine 2u over 2. Right? So, and there are a couple times in life where you might not want to deal with sine squared of u, right? Like graphing, someone asks you, hey, graph sine squared of x. You'd be like, I don't know how. But I do know how to graph 1 minus cosine of 2x over 2. That'd be one example. There are also some things in calculus that are hard to deal with, but in the squared form, but maybe not in the other form. So the other couple applications that come up in life, but we'll just go with it for now. Right now it's just kind of a mathematical curiosity, but it will serve us very well in the next slide too, so you'll like it. Likewise, very, very similar. One of the other formulations for the cosine double angle formula on the previous slide was this one. And that admits a power reducing identity for cosine if you solve it for cosine squared. You get, instead of 1 minus cosine 2u over 2, you get 1 plus cosine 2u over 2. So that's how you might deal with a cosine squared. And tan squared will do a power reducing identity for tan squared and derive it in a slightly different way. We'll just use the two results we just got and divide. Sine squared over cosine squared. All the 2's go away, and in the end we just get this. Wonderful. Let's put them in a box. All right, so now what do we have here? We got the double angle formulas. From the double angle formulas, we derived the power reducing identities, which are like, kind of useful, maybe. I don't know. Don't worry, we only have one more set, right, Alex? Okay. One more box to show you in your whole identity life.
And then are we done with identities for good?
Yeah.
I will never at the end of done because I'm sure someone has come up with that.
You might already be happy about it. Can I just want to give people time here to absorb this. I've showed you a lot, pretty rapid fire the last 2 slides, so please ask me if there's like a algebra question or a notation question or a like, what did you just do there? Why is that arrow there question? Anything question. Like, let's just give everyone a moment to absorb this. Can you give everyone some psychological space, you guys? Just give people some room to study the new information. Let it sink in. Just let it sink in. And if you have a question, let me know. All right.
So if you see, like if you just see tan squared u, can you jump to this, or do you have to show all the work?
Oh no, you never have to show the work here. I just want you to know how to, if you forget them, to rederive them pretty quickly. Yeah.
How will we? How will we?
I just did. So do you agree with this statement?
I don't think I'm gonna run across it anymore. I don't get the real with it.
I mean, everything we've shown you is improved by over time here, right? You're improving it, the first principle. Yeah, it's a corollary of the previous thing.
That's the only.
All right. Now consider sine squared of u over 2. Do you still need this for a second, Noah? You good? All right, listen, please. Can you guys stop talking? Noah's going to ask the question first, and then I want to talk about the half angle identities here. Go ahead, Noah.
Okay, so if we see like 1 minus 2 sine squared u on a test, would you expect us to know about like cosine 2u?
Sure. Cosine squared, cosine 2u. Yeah, you should know these identities for sure, in the end. And just by doing some of the assignments that we're asking you to do in the homework, you will learn them, right? Just by practicing them.
Oh, excellent.
So sine squared of u over 2. Let's like just think about what that is. And we're doing these 3 identities today, these boxes that we're presenting to you on the first slide and the second slide, and now here comes the third one. In this order for a reason, right? We just did an identity called the power reducing identity for sine squared. And what was that? Well, it was this, right? If I plug in a u over 2, though, I get the following. Or if I simplify, I just get this, right? If I plug in u over 2 into the sine power reducing identity that you just wrote down a second ago. Am I right? Okay, so now ignoring this part in the middle for a second, right? Just like block this out of your mind. What do you see here? You see sine squared of u over 2 equals 1 minus cosine u over 2. Now, taking that equation and taking square roots on both sides gives us, just over here, sine of u over 2, and we call that the half angle identity for sine. Okay? Now, why is this useful? Well, one reason this might be useful is like, you want to find the sine of 22.5 degrees? Of course you do. Well, that happens to be half of 45 degrees. So, what is the sine of 45 degrees over 2?
22.5.
It's equal to the square root of 1 minus cosine of 45 degrees over 2. And the cosine of 45 is something we know. So this allows us to find, instead of, allows us to find the trig function, in this particular case, the sine of an angle. When we don't know its sine, we only know things about the twice that angle, right? So like, would you like to find the sine of 22.5 degrees is a nice one to reach for. But we could do a whole bunch of other ones too, like how about 15 degrees? We talked about that yesterday, how we could use or on Monday, how we could use the sum and difference formulas to get that. But couldn't you also find the sine of 15 degrees from this, knowing that you know what you know about 30 degrees? Right, so that's one very powerful application of this sine half-angle identity. The cosine half-angle identity is derived in the identical way, using, again, the previous slide's power-reducing identity for cosine. You get almost the exact same result, right, except with a plus instead of a minus. And I should say, too, that this plus or minus out front is a little bit like of a sticky issue here. Let me just say something about that. Because in the end, I know sometimes we think of plus or minus as meaning and. It means we get two answers. Well, of course, the sine of any angle is a function. Sine is like a function. It only returns one value. So it's not like we get two values here. For example, the one I was just thinking of, the sine of 22.5 degrees, or the sine of 45 over 2, is that positive or negative? Even though you don't yet know what it is, you do know that it's got to be positive, right? So I just want you to be aware on these two. Just be really careful that you don't just like apply these formulas indiscriminately. In the end, the answer will be either positive or it will be negative, and you need to do the work. If the formula doesn't just hand it to you, you need to do the work about thinking about, okay, this is in which quadrant? Before you ever do anything with a trig with an angle, you should know the sine, the SIGN, of its sine, SIN, right? Before you ever begin. And then the tangent half-angle identity is, here's one way to write it, and I want to say more about that, but that's you on an interlude. Interject. Go ahead.
I was wondering, where would you use this?
I know, this comes up all the time in math, right? So, first of all, I should say, yeah, do I want to answer that right now? There's lots and lots of trig that is useful to you. Have you found that to be true yet? Or are we throwing out all of the 3 units of trig? What do you think? All right, so I'll just say this. Anytime in physics or in math or in life where you meet a triangle, or when you meet something, that was like unit 3, or what we call, no, unit 4, excuse me. Anytime we meet a triangle, trig is right there with you. Anytime you meet a circle, trig is also right there with you. Anytime you have something moving in a circle, trig is right there with you, right? So I know you guys haven't taken a lot of physics yet, but certainly in physics we talk about like uniform circular motion, and we're tracking the position and the velocity and acceleration of a particle moving at a constant velocity in a circle, and we want to think about like it's the things we've been talking about in this class, things like the frequency and things like that about the particle, but then things we'll talk about in calculus too, like the rate of change of things happening with that particle, like its velocity, acceleration, and the direction of those vectors of motion. All of those are governed completely by trigonometry. I was talking with a friend of mine after class yesterday, asking a similar question, and I challenged you to do the following: write a program. Do you know a programming language? You don't yet, okay, but you're gonna learn one tonight, maybe. Okay. So, like, pick your favorite programming language and give me a program that like takes a particle, a little ship or something, a little graphic of your choice, a little smiley face, whatever you like, and sends it around in a circle. Try it and see if you can do it without using trig functions. And I guarantee you will fail. You have to use a trig function to describe. I'm just saying. I'm just trying. Try getting a particle to go around in a circle on the computer without using trig functions. Or, for that matter, try drawing a circle on an Etch-a-Sketch without using trig functions. Yeah.
Just use.
What's that? No, yeah, and I'll say something about that. I have Now, Vesh, there are a lot of good answers to your questions about like where trig arises in life. That's for sure. But then the other question I have for you is like, is that the only thing that matters to you? Is like whether it matters in the real world? Because math, no. Because I want you to understand, like when we're proving a trig identity, we're proving something that is way, way bigger than yourself. You understand? Like when you establish that truth, that's like a truth that will live on forever. Whether even after you die, that'll still be established truth, right? Like and so when you're doing this math, it's like these puzzles. They're fun. They're interesting in their own right. Math is beautiful in its own right. Sometimes later, way after someone dies, it's proved useful. But does it have to become useful someday to be important and beautiful? Like no. Almost always, it becomes eventually useful. But you started this, not me. Okay. I just want to like share my perspective that someday some things, and that's been true even like think of Einstein at the turn of last century. We now understand space to be modeled by a curved model, right? So we don't think of it as Euclidean anymore. And the nature of space-time being curved, that was described mathematically way, way, way before it was ever became useful. And at the time, people might have been like, "What is this good for?" And the person doing that would have said, "I don't know. It's just mainly fun. It's beautiful. It's interesting." And it's true, right? Whether it applies to the real world or not is neither here nor there. So I like doing math because we get to study a set of objects that are beautiful and interesting, and we can prove things that are ultimately true. And that's not something you get to do in other subjects. In other subjects, like even in science, which is like a hard thing, the idea is you collect evidence and then you suggest with strong conclusions that maybe it's true. But in math, we don't collect evidence. We do deductive proof, like every single step of the way, everywhere. We're proving things to be true. So I think that's a beautiful aspect of math that I just want to share with you, and you get me going, man. All right. Yeah. What's that? Yeah, if you computate like theory of computation. I like yeah. So anywhere where you have a domain or logic, yeah.
Whether it's true is
Because it was in the past tense. Here, let me throw some stuff up here. All right, now I've set you off. All right. One other nice way to write this formula for the tangent of a half of an angle is one of these two ways. Can you follow my arrows? So either way is fine. This first one, I'm multiplying underneath the radical by 1 plus cosine over 1 plus cosine. That creates for us something that's a perfect square in the numerator and in the denominator, and then the square root goes away. And so that's kind of elegant and beautiful. So that's another formulation for the tangent half angle formula. And does it matter that the plus or minus is there? Actually, it is not a typo. We can drop that, but especially because we talked about that other stuff for a little while. We're not going to explain why. You can look. There's a little explanation in the book. Maybe you can reason through the graphs of these things or plugging in values. You can see that actually the sign of this you don't have to worry about like you did on the first two. These two expressions, if you just plug in a u value here, it'll come out right.
So tangent, whatever gets you to that at the end?
There they are in a box. Good stuff.
So it gets you to that, tangent gets you to that at the end. Gets you to that.
Yeah.
Oh, okay. So we don't have to do that. Can you go back for a second? No, it's right here.
No, it's
All right, I have an early holiday present for you here. Oh my god.
It's the best message ever. Trick sheet, treat. Not all that shit. He's gonna be like 2 minutes to look at it. Dude, what if there's a
I mean, for the semester exam, I'll talk about that here. All right, listen. I'm giving you. Stop talking books for a second. This is not made by me. This is made by Paul Dawkins. This is his name. I stole it from him. It's 2005 copyright there. So the reason I say that is that not everything on here matches perfectly the things we've done. So, but it is a pretty pretty nice summary of like all the things we've from all 3 units of trig. Like basically everything people might say about trigonometry all in one place. You know, you see the unit circle is even there, and some triangle pictures and log signs and stuff like that. But you can see there's some things we haven't studied as well, and you're not responsible for those in addition. It just happened to be on this other person's sheet that I gave. So like, notice there's a law of tangents, for instance, that we haven't studied. But you can feel free to look at those on the front, or on whatever this is. There's the sum and difference formulas. We know those. But then there's like a product to sum formula and a sum to product formula. You don't need to know those, okay? They're there though. Also notice that the half angle identities that I gave you are actually not there. You see they're up on the screen here, but when it says half angle formulas, it's actually giving you the power reduction identities that I gave you. So it's not wrong. It's just like, I mean, they are basically the same. Just take square roots and boom, you've got your half angle identities, right? So whatever. I'm not too worried about that. Anyway, they're all formulated a little bit differently. You still may want to like write them down in the way that we're presenting them too. However, in the end, you know, just math works, so do whatever you want to. But yeah.
I just have a little question. So we write plus or minus as a plus over minus, but here it is one greater minus over plus.
Yeah, so I think I mentioned that in the class the other day that if you want to and you want to be slick, then by minus over plus, like you're thinking about the cosine sum formula, sum of difference formula, the minus over plus means, hey, whatever you chose to be true in the first set of parentheses, the plus, if you chose that to be a plus, resolve this next one as a minus, right? Does it make sense? Because if it's like cosine of alpha plus beta, then over there it's going to be a minus, right? So, all right, let's start using some of these here. So now that we have all of the identities in full view that we're going to ask you to know, and by the way, this is fun and useful, but you're going to need to, I will ask you to know them. Any formula that you found useful and you want to know, then you should commit to memory for this test, at least, for this upcoming test. The semester exam, we give you all sorts of formulas, don't worry. But, all right, we're supposed to solve this equation here. Now that we have all these identities, we can do all sorts of things like solve equations, prove stuff, you know. So this is nice. We now know how to deal with sine of 2x, don't we? How do we do that? What way do we write instead? Thinking about even our warm-up today, you guys did it. It's 2 sine x cosine x, and then the rest is history, right? So we get 2 sine x cosine x minus sine x equals 0, right? I mean, the rest is, that was the interesting part, right? I don't really want to labor over the rest of this because we've done this a bunch of times, right? On the interval 0 to 2 pi. Like I said, the rest of this problem doesn't really interest me, so I just bang out real quick like that. But are you okay with that first step especially? This right here is the part that's kind of new, right? That idea of using the double angle formula. The rest is not that interesting to me though. Okay. It's time for a joke. Why couldn't identity sine of 2x equals 2 sine x get alone? That's right. It needs, what does it need? It needs a cosine or, yeah, that's right, okay. That's hilarious. Come on, okay. All right. Is that a good intermission?
It was like left-hand side X. Yeah.
All right, I'm gonna kind of rush through the last couple examples here. I want to make sure we get to these. So stay with me, please.
2 pi.
Cosine of 6x, we're asked to prove that that's equal to this, apparently. And if you just stare at this for a second, I'm going to give everyone silence for like, how about 20 seconds of silence before we say what? We don't want to give any spoilers. And then I just want to stare at you because let you stare at this because I think it's stare at you. I'll stare at you while I stare at this. And just to see whether you think this is obvious. Like once you stare at it for 20 seconds of silence. Ready to go. Think about it. Nope. Stare at it. You can look to your notes too if you like, or your trig identity. You see it? Once you see it, the proof is almost immediate. Here, I mean, there's not much to prove, in fact, once you see it, right? So, did you see it? I just didn't want to spoil it for anyone. So the left-hand side is equal to cosine of 6x. That's terrible. I don't know how to. This board, man. All right. Is equal to the cosine of. Yeah, that's gonna really work well, huh? 2 times 3. Oh my goodness. I don't know what to do. I don't know what to do with this board.
Go to the whiteboard.
All right, people online. Sorry, I'm going over the whiteboard. All right. So cosine of 2 times 3x is what we have on the left-hand side, and then the result follows immediately, right? One of the formulations for the double angle formula is the following, right? Cosine of 2 times something is equal to 2 cosine squared of that thing minus 1. I just don't know what else to say. Right? Okay, that's why I said just stare at it for a second and it just appears to you, right? Okay. Let's prove one that's not quite as trivial. All right, I'm going to take this a little bit quicker than you might like, but we're kind of getting short on time here, so I want to.
Oh, because you went on that tangent.
Justin,
All right, I'm going to start with the left-hand side here. Sine of 3x can be expressed as the sine of x plus 2x.
Yeah.
And then I'm going to use the sine sum formula, which is sine of the first thing times the cosine of the second thing plus cosine of the first thing, sine of the second thing. So here we go. Sine of the first thing, cosine of the second thing, plus cosine of the first thing, sine of the second thing. Using the sine sum formula. And now I'm going to use the cosine and the sine double angle formulas to resolve these two expressions. So this is 1 minus 2 sine squared x is one of the ways you can write that. And over here, this is 2 sine cosine. See how you just need to know these? I don't know how to tell you. Okay. You could use one of the other formulations for cosine 2x if you like. Why might I be choosing this one though? Keeping the target expression in mind. I'm choosing to write this as 1 minus 2 sine squared x, this guy right here. Because in the end, what do I see and what don't I see?
You don't see any cosines.
I don't see any cosines, so I'd like to maybe just keeping the target expression in mind. Eventually I don't want to see any cosines. So that's my project right now is to So in that same spirit, can I deal with this cosine squared over here somehow?
Yes.
I'd like to have everything in the end be in terms of sine. So how about we want something in life, we make it happen. Are we having fun yet? Okay, let's see here. acting like terms gives us 3 sine x minus 4 sine cubed x, and the result follows. Right? Okay, so like I said, I apologize for doing that really quickly, but I want to say something about this last example too. So I'll let you stare at that for a second and ask a question. So the double, there's a whole bunch of algebra at the end, but the sine sum formula and the double angle formulas are what I mainly use there. And then I'm just like doing some algebra again. Okay? So the point is, sometimes these proofs might be obvious and sometimes not so much, right? But I mean, I mainly just went to the trenches on that one. I just was like, let's do this. There's one last thing that I think is kind of critical for us to understand, and that's how to resolve this expression, or ones like it. I already hinted at it today, but I just wanted to at least actually maybe think with you about how to set this up. I don't know the sign of 5 pi over 12, but I do know this. I do know how to deal with 5 pi over 6, don't I? So if I think about this as this 5 pi over 6, then I can use the half angle identity for sine. And 5 pi over 6 I already know has, 5 pi over 12 has a positive sign value, right? It's in the second quadrant, so, it's in the first quadrant. So it has a positive sign value. So what is it? It's the square root of 1 minus cosine of this thing, 5 pi over 6, over 2. I just copied that right off my formula sheet just now, right? Yeah?
Yeah.
The cosine of u over 2 is equal to this. The sine of u over 2 is equal to this. And all of this stuff we know how to deal with. Cosine of 5 pi over 6.
So 1 plus 3 root 2.
The cosine of 5 pi over 6 is negative root 3 over 2.
Divide by 2.
Yeah. So if we multiply by 2, what do we get? 2 plus root 3 over 4.
Please come to the main office.
All right. Fairly well. See you tomorrow. Homework 7 tonight, please.